All right, guys, we're going to look at lesson 22 now, which is just going to be continuing bonding. So the first type of bond we're going to look at here, we've done a lot on covalent bonds. That's where we drew the Lewis structures before the last test. And now we're going to look at an ionic bond, which happens when one atom loses electrons and the other atom gains electrons. And so if you take something like sodium, Na, and chlorine, I have their electronegativities written here. So you look at Na, sodium, has a low electronegativity, so it's happy to give electrons away. Chlorine has a high electronegativity, so it wants to take them. So what will happen, the chlorine will steal the electron from the sodium. That's what's going to happen. So sodium gives an electron and chlorine takes it. And so what's going to happen, we're not going to have the structures. We're not going to draw the pictures like we did for covalent compounds. Instead, what we're going to do, we're going to have cations and anions bonded together. So positive ions, so the ones that give away the electron, and the anions, the ones that get the electron, are going to be together. And we make a ratio of how many cations we need for every anion. And that's called a formula unit. So a formula unit is just going to be one of these ratios, which, like right here, if you look, the first question, here's just a bunch of formula units right here. See, they're just a bunch of ratios of how many Li's and how many F's you're going to end up having. And so the way that we're going to figure this out, if we have something like sodium and chlorine, it'll be NaCl. Calcium and fluorine will be CaF2. So let me show you how we're going to figure this out. You're going to go to the periodic table. All right, and from the periodic table, you're going to look at right here. If you've been doing what I said to do a while ago, where you print one off for yourself and then you write the pluses and negatives on here, you need to remember that group 1 all has a charge of +1. Okay, meaning these all want to lose 1 electron, so they're typically going to be +1. Group 2 is going to be +2. Over here, 13 is +3. 14 can be +4 or -4, and so they actually usually just share. These are only involved in covalent bonds. And then right here, 15 is going to be -3, 16 -2, 17 -1. And then 18 is just 0. Nothing happens with these. They're too lazy. So remember what the charges of each of these are. So what's going to happen when we do something like this, let's do sodium and chlorine. I'll just write it on here for you to see. So if we have sodium Na, what's the charge of Na? So sodium, Na, it's in group 1, so the charge of it is +1. So Na is +1. And then what is the charge of chlorine? Cl. Let's find Cl. Cl is right here in group 17. Everything right here is a -1. So Cl is -1. Now, do +1 and -1, do those cancel each other out? Yes, they do. That's why the answer ends up being NaCl. You just need one Na and you need one Cl. So just NaCl. Now let's do calcium fluoride. So calcium, Ca, let's look at what it's going to be. It's right here in group 2, so it's +2. So Ca is +2. And then fluorine is over here, and it's going to be -1. So fluorine is -1. Okay, so let's think about, is this balanced right now? No, it's not. What we need is do we need more calciums or more fluorines? We need more fluorines. So if you do another fluorine, it's -1. Does -1 and -1, what does that add up to? That adds up to -2. And does -2 counteract +2? Yes, so it's balanced. But in order to balance that, how many did we need? We needed 1 calcium and we needed 2 fluorines. So it's CaF2. Let me demonstrate the hardest type for you. Let's do an Mg. So let's do Mg, and if we have N, let's do Mg and N. So Mg is +2. Right here, Mg right here, it's in group 2. Those are all +2. N is in group 5. Remember group 15. So these are -3. So N is -3. Now, how do we balance out a +2 and a -3. Well, right now we have more negatives than positives, so let's get another mg in there, mg +2. Well, now it's going to be +4 to -3. So the negatives need to catch up. So let's get another n in there. Okay, now it's +2 and -6. So let's do another mg. Okay, now look at add that all together. +2, +2, and +2. We have a total of +6, -3, -3, and a total of -6. +6 and -6. So the charge is balanced out. How many of each was needed? Well, for mg, let's see, let's do let's do this. So mg, there was 1, 2, 3 of them. There was 3 mg's, and then for the n, there were 2 of them. So mgn2 would be the formula unit there. Okay. So now I want you to pull up your periodic table if you need to, and try to do these first 4 questions where you predict the formula units. So press pause, try them yourself, and then I'll go through them with you. Okay, number 1, Li and F. Li is +1, F is -1. +1 and -1, we are okay with just LiF, one of each. Number 2, Be and Cl. Be right here, this is going to be +2. Cl is -1. So we need 2 of the Cl's. So it'll be Be, Cl2. Mg and S. Mg is +2. S is going to be -2. So 1 of each. So we're happy with just MgS right here. And then lastly, K and N. So K is +1. And then look at N over here. It's in group 15, so it's -3. So -3 and +1. We're going to need 3 of these K's to balance it out. So it'll be K3N. K3N. Okay, the last of these, you're going to be writing out answers to these questions. But let me run through the slides with you, and that'll give you suitable answers to these questions. Okay, so what will happen when you have ionic compounds, because you're going to have positive and negative sides, they don't just randomly pile up. The positive sides will want to get away from the positive sides, and then the negative sides get away from the negative sides. So what ends up happening, they end up in this perfect little row, and we call these little rows the crystal lattice. If you look at crystal lattices, like if you look into a crystal, it almost looks like there's all these little squares in there. And it's because there kind of are, because everything ends up in a box because the plus wants to get away from the negative. So all these molecules end up in this orderly arrangement. They don't want to be in these weird diagonals and on top of each other. They want to be in this orderly arrangement to keep the positive sides away from the negative sides. Okay, now metallic bonds, we're not going to have to do a formula unit or any type of a Lewis structure, because with metallic bonds, something completely different happens. They all have low electron affinities. So what will happen is metals, they're not going to be fighting over electrons the same way that you're going to get in a covalent bond with the nonmetals. So what happens is they're not going to be taking electrons to fill their octets. So a model that explains how this works is what we call the electron sea theory. And what this basically says is that because they have low first ionization energy, what will happen is the outer electrons are basically leaving the atom, and then they can just be attracted to the nucleuses in the other atoms around them. So basically what happens is the metallic bonds work because you have all these free-floating electrons on the outside of every atom that are then attracted to the positive nucleus of the other atoms. So it's like a big like hippie commune where they're just sharing all these random electrons all over the place. So that's why you end up having a large number of atoms in a metallic bond. So this chart just kind of explains them. Non-metal, when it bonds with a non-metal, they're going to share the electrons because they're fighting over them, and you get a covalent bond. You're either going to have low to medium bond polarity, because normally you have negative in the middle and a positive on each side. When you have a metal to a non-metal, you're going to transfer the valence electrons. So you're going to literally give one electron from one to the other. So it's going to be very polar. We call that ionic. And then with a metal and a metal, there's not even really polarity because they're not fighting over the electrons. They just share a whole bunch of electrons between them. With covalent compounds, because look right here, covalent does not have very much polarity. And remember, bond polarity makes bonds stronger. So what happens is you're going to have weak forces holding the molecules together. So it doesn't take very much energy to separate them. And so what will happen is they're not very dense. It's supposed to be not very dense or hard. The exception to this would be when you have a network covalent substance, which is when covalent bonds make a 3D network, and that's what you get when you have diamonds. Properties of ionic compounds. With these, what will happen is you have very, very strong ionic bonds, so you have strong electrostatic forces, and so what will happen is the compounds are dense and hard, and it's really hard to melt them. What will happen is they can be brittle due to the fact that they're in tightly bonded rows. So what will happen is you can fracture one row off. So they'll be strong, but the pieces can be chipped off. And then lastly is if you have metal-metal alloys, because you have all these free-floating electrons in a metal bond, they're really good conductors of heat and electricity because the heat and electricity can travel through those outer electrons. And so instead of everything being packed tightly together where everything is stuck in one way, you have these free-floating electrons that can pick up heat and electricity. So that's just kind of the read through those again and make sure you understand them and then use that to explain these answers right here. And then once you do that, then you are done.